Welcome back, everyone. My name is Daniel Sills, and this is the midterm check-in video for the University of Louisville Applied Robotics course. For those of you new to the series here, our class goal for this course is to build an autonomous submersible robot capable up to the midterm of submerging itself and re-emerging back to the surface in a controlled and regulated manner. And this midterm is a collection of videos and evidence showcasing my work that I've done in order to create a robot that achieves this goal. So the agenda for today's video is to go over the CAD designs that went into making this robot, then present the hardware, how the CAD was actually executed and what I've managed to achieve, and then discuss the design principles and the testing and the concepts that went into to fine-tuning the robot and its functionality, and then finally give a functionality demonstration from beginning to end of boot up, execution, and submersion and re-immersion. All right, let's get into the CAD overview.
All right, so welcome to SolidWorks. This is where I've done the majority of the CAD modeling for this project, and so we can start to look around and see some of the defining features that we've already come to know about this robot. We've got our two ballast tanks on the side, we've got one of our pump housings up here, and we have our central body right here. The big benefit of doing a lot of this in CAD is that, well, it's the only way for some of the 3D printing, so it's hard to say that it's a benefit. But the primary use, I should say, of doing this in CAD is so that I can 3D print some of these components. And so the goal here has been to model the parts that we need in order to base other parts around them. And so you can see that we have our central PVC body that is clear in the center, and then we have our two ballast tanks and just one of the pump housings. This part, let's see, where does it? This part, which mounts the pump housing, can be flipped around and used identically in order to mount the other one, so it does not have to be remodeled. So I guess let's just go top to bottom. And so I'm going to go ahead and hide all of our pre-built components. And so these would be anything made out of PVC pipe, or I do have a model of our pump in here, and I'll explain that here in a moment. And the last one here. And so you can see that we have this central chassis here, which I'm actually going to go ahead and hide. Just because we're not ready to talk about it yet, because I want to talk about our external chassis components first. And so this triangular one here is for mounting the PVC pump housing. And so it nests between the ballast tank and the main body. And so it has radiuses to fit both of those. And then this other one mounts our main body to our other ballast tanks. And so it has the radiuses to match those as well. And so a big thing that you will see is the adhesion mechanism that I'm using between PVC and 3D printed parts, as well as from 3D printed part to 3D printed part, is zip ties. And so these all have channels so that zip ties can go through them so that they can be mounted together. And so hiding these again, actually I'll leave our center body. I'm going to hide all of these. And one more. And then I want to pull up, yes, this one. And so this is the, you could call it a lens frame, is kind of a good term for it. So the plan here is to have a piece of acrylic across the over the end of the PVC, and so this is to give a mechanical mounting point. And so I'll discuss this further in the hardware overview, but this is glued onto the PVC pipe and will hold the acrylic sheet in place that is over the end of the PVC pipe. Super simple part, but I think it adds a lot of rigidity and it came out really nice. The big thing here was I wanted the tolerances to be super, super small. So it did require a little bit of experimentation with the 3D printer in order to make sure that I could get, this is a 0.1 millimeter tolerance around the PVC pipe. So it has a really good friction fit. All right, so hiding that again, I will bring over the pump models. And so the big significance of these is sometimes it can make it a lot easier to model something if you have something that is a rough shape of the part. And so the gray part that you see in the back is a good representation of the pump motor. And then the blue part at the front is a good representation in a rough way of the pump itself. And so this, in combination with the pump housing part, is what I used in order to design the pump chassis or the pump mount. And so I will actually have to take you over to KURA in order to showcase that. But essentially, it's working off of this concept that by tilting this this pump backwards slightly, we can take a lot of the pressure off of the hoses that come off of the peristaltic pumps. And so that can prevent kinking, and it's actually worked really great. I haven't had any issues with the pumps, and so I'll take you over to KURA and show you what that looks like now. All right, welcome over to KURA. KURA is the program that I use for exporting 3D files to my to G-code for my 3D printer. So this is a 3D file of that pump mount that I was talking about over in SolidWorks. Unfortunately, I have had awful luck with this design, and each time I have modeled it, which has been probably 2 or 3 times now, I've had some kind of file issue, save error, something along those lines that has meant that I have managed to export and print this a number of times, but I have not managed to save it within the CAD design. So I do have this STL version. So I do have it where I can print it if I need to replace it on the physical device. But I do not have it where it can be incorporated into the CAD design, unfortunately. I could reverse engineer it from the STL file, which I may do at some point in time. But for now, I just wanted to demonstrate the functionality of this. It has a series of mounting holes for the motor for the pump, as well as the exterior 4 mounting holes for the pump itself. It clips onto those holes, and then it has central screw holes for the motor. And then you can see that it is a cylindrical shape, and so this allows it to not twist or not twist inside of the pipe, but remain at this angle. This angle has been hugely beneficial to making sure that the hoses that come off of this plate at a parallel don't end up getting kinked or bent too hard as they have to go to the exterior of the pump housing. So I'll go ahead and take this opportunity to showcase some of the print settings that I've been using. I use a layer height of 0.12. This has been a good middle ground between fine and coarse printing, as well as my printer has a Z-step height of 0.04 millimeters, and so I find that I get better Z performance if I go ahead and leave my layer height at an interval of 0.04, and so of course 0.04 times 3, 0.12. So I've been using an infill density of 20% with a gyroid infill pattern, and I have been bouncing back and forth between a skirt and a brim depending on the bed adhesion that I'm able to get on any given part. This one I do believe I ended up printing with a brim. All right, coming back from KURA, I have one of my internal chassis components modeled up here. And so I think that this is a good example of what a baseline chassis component would look like. We have this tray in the bottom, and so this is where we can hold bulky components, or it's where we can hold weights. And so that keeps our center of gravity really nice and low. And then it also provides us a nice mounting platform for any of our electronics. And so it has this ring that goes all the way around because that helps to solidify its place within the tube. With this ring in place, it can't rotate or rock or fall. And so anything that's mounted to this should be held in place pretty well. It will have the ability to rotate, and so but I think there's a world where, depending on the distribution of mass, that could be a good thing, where if the robot is at a slight angle, it could act as some kind of mechanical stabilization for the camera, potentially. But that'll have to be accounted for in the controls, obviously. Another example of utilizing these slots would be used for zip tying the components together, which I'll go over in the hardware overview. And so I will go ahead and pull up another version. And so these could be zip tied together right there at that interface in order to link them together. And so now I'll go ahead and get into the specialization of these components. And so I'm going to turn off our outer body here just to make it a little bit easier to see. And so these last two have been specialized. You can see that I've cut out a ridge right here. These last two have been specialized in order to house our big bulky battery. And so it's got this hump at the top that requires a little bit more height. The rest of the battery fits under the platform here. And so you can see that these slots, so it can zip tie together. And then on top, we have our Arduino mount. And so the Arduino would be mounted on top of here just to keep it solid and out of the way. And so these two components are actually what made it into the midterm version of the submarine. I'm looking to add a third, potentially a fourth, depending on length. I do think this is out of the length spec, which I will talk about the change that I made there later on in the video. But I do think that this is currently out of the length spec, so I will have to do some redesigns, probably to the Center 3 components, as I'll need to relocate the Arduino in order to better accommodate the Raspberry Pi for the back half of the project. But for the time being, these two are the components that were deployed, and so I will show you them in the hardware overview.
All right, and moving on to the hardware overview.
All right, welcome everyone. Here she is. This has been the most convenient way to store it. So I'll go ahead and remove it. This also acts as a nice drip tray for whenever I take it out of the tub from testing. All right, so in its upright configuration, how it will be in the water, it'll look about like this. And so I'm gonna go ahead and put it back up like this. You can see the pump housings and then the ballast tanks. And so typically I plan to operate with the ballast tanks down in this configuration. All of this can kind of shift and move, which has been really helpful with getting the balance just right. So we have our battery, and so this is the main power for the entire sub. And so let's go ahead and remove the internals, because I think that's the part that we really want to talk about. I will go ahead and touch on, you can see all of the 3D printed components. This is a 3D printed component that I have PVC cemented onto the PVC housing, and then I have used a Gorilla Glue sealant on the acrylic right there. And then each of these, you can see there is a 3D printed component, 1, 2, 3, and 4 for the other pump housing. That is actually the easiest way to see those pump mounts. All right, so let's lift this guy up. Luckily, with it being PVC, it is incredibly rigid. I think my primary fail points are definitely my 3D prints. Everything else is super, super strong. The zip ties obviously are kind of a, it's an industry used item, so obviously it's quite good at what it does. All right, so here it is. I've been using these modular ankle weights in order to provide additional weight for the system. This models some of the additional components that I plan to add later on, as well as just helps me fine tune and create bigger margins for the ballast tanks, which I'll talk about later on in the video. So we have our battery cable running into our motor housing up here at the top. We then have two motor cables running to our pumps. These two motors will be used later on for the thrusters. We have an additional weight here at the front that's been zip tied on, and then through the bottom of this chassis we have our 8.5 volt nickel metal hydride battery. This is a battery designed to be operated with Traxxas RC cars that I was able to commandeer for this project, and it has served me very, very well. And so this is a motor shield running 297, I believe, 297 motor controllers into an Arduino, and so it uses a standardized Arduino library to run those. That's very, very simple, and I will showcase that in the functionality video. I guess another thing to talk about here is, I'm going to go ahead and leave that here, is these are all through wall mounts, and so they go to another barb on the side of each of these. I can showcase one of those here. And so this is great because they can go straight to a pump on the other side here. And so there's another hose that runs through and out to the other side. And then here I've actually utilized it so that there's another length of hose here, which will hopefully dangle with gravity to the lowest point in the tank, making it more likely, especially on the sucking motion, when we're trying to pump water out of these, that it will actually pump out water and not just air. So something I would like to replace after the midterm would be all of these hot glue joints. They have worked okay, but not great. I have had one joint that I think has been a stellar performer, and that has been this one. I have replaced this joint probably coming up on 3 or 4 times, attempting to get it just right, and I still haven't. This is probably the slowest leak that I have, but it is still a leak, and so obviously this doesn't have an infinite runtime, even though the battery would die. But and then this one is benefiting from having the this one does have a leak, and so we do lose a little bit of mineral oil, especially as it's in open air. I feel like we drip more than whenever it is in the water.
All right, let's get into the design principles. This is discussing the buoyancy and other things that went into making this design a reality and how I came up with some of my ideas. So first of all, I presented this buoyancy design from video check-in 1. It has a number of problems, the primary of which being it did not account for the actual mass of the PVC pipe, and it also was working too much off of some assumptions based off of including the mass of the ballast tanks, and it also did not include the mass of the mass and air mass of the mass and displacement, that would be, of the pump bodies. So I kind of would like to redact this and instead replace it with this. And so here is a better buoyancy design based off of today's robot. And so here, instead of looking at the just the main body and the ballast tanks, we are instead looking at the main body and the pump housings. Ballast tanks will come in later and are primarily just serving to offset the mass and displacement of the pump housings and the main body. And so these measurements have been adjusted to reflect the actual diameters of the PVC pipe themselves, and some of these weight measurements are actually based off of real life measurements that I've taken. So first of all, we have the pump housings come in at a volume of 25.77 cubic inches, and the main body in this 12-inch height configuration comes in at a volume of 190.85 inches cubed. This produces a total volume with two pump housings of 242.39 cubic inches, and weighing this configuration with some of the supporting structures and other things that I added in that you saw in the CAD design. And so this is without weighing the included the ballast tanks. I removed them for this measurement. It comes to a mass of 2,698 grams. So this gives us an average density for this entire configuration at 11.13 grams per cubic inch. And this is in contrast with the average density of water, which would need to be greater than of 16 grams per cubic inch. So this gives us a necessary mass that we need to add into the system or subtract, or the necessary mass in order to be heavier than water would need to be 3,878 grams, giving us a difference of 1,180 grams. And so I'll get into some of the things that I have done in order to compensate for this. So the two big things that I've done to accommodate for the weight that we need to offset is the first is I've reduced the body size by 3 inches from 12 inches down to 9 inches. This gives us a change in volume of 47.71 cubic inches and reduces the mass that we need to accommodate for by 763.36 grams, which is a huge improvement. And so the second thing that I've done is I've filled the oil pump housings with mineral oil. So that is these two housings, and I've filled it with mineral oil. Mineral oil is a non-conductive oil that's commonly used for oil-cooled consumer PCs, like you see in the fish tank on the right. And so it has the benefit of being non-conductive as well as being an oil, and so obviously it doesn't mix with water, and so that makes it resistant to displacement by water at small interfaces. This is a tip that I picked up from a waterproofing a servo motor tutorial that I watched. And so mineral oil has a density of 13.1 grams per cubic inch. And so by filling both of these motor housings with mineral oil, we produced a mass change of 370.47 grams. And so adding these two together, we have more than made up for our weight accommodations. And so coming back to our ballast functionality, if we take into account all of the changes that I've made, in order to compensate for our difference in weight, it gives us a neutral buoyancy target of 1,564 grams. And so that means that with the ballast empty, we want our total mass to be less than that 1,564 grams. And with the ballast full, we need our total mass to be greater than 1,564 grams. This is in addition to the added mass from the ballast tanks, which should relatively compensate for themselves as they will be completely empty vessels. And so here's where we kind of get into an interesting discussion where the rate at which we want our robot to sink is highly dependent on the amount greater than or less than that 1564 number. So if we want our sink rate to be relatively slow, then we only have to hit 1565. Or if we want our rise to the surface to be relatively slow, we only have to hit 1563. And so we have, even though the pumps, as you'll see in the functionality, are relatively slow, if we can manage to get our ballast calibrated correctly, it will mean that we only have to move our ballast a very small amount in order to just tiptoe around that line of neutrally buoyant. So, and so the other thing is, if we were to hit a sweet spot of neutral buoyancy or be very, very close to that 1564 number, like I was saying, just grams, then that would allow us the opportunity where we could use thrusting instead of having to rely on our ballast in order to move us up and down within the water, which is a part of the future plans of the robot. And so I've got this note that says it's all about getting the right volume of water in the tanks. And so that's where I come back to. We have this graphic on the side, which showcases level 1 and level 2. Somewhere in the middle may be that 1564 gram mark, but level 1, it would confidently float, and level 2, it would confidently sink. It may just be at a very, very slow rate. All right, and for the last section of the video, I'm gonna pass it off for a functionality demonstration. So let's see if it works.
Okay, so I have a basic program here. This is mainly just timings and delays. So we're using the motor driver library from Arduino. And so it just has this, we relabel it to M, so we can do m.motor. And so they're numbered 1 through 4 on the driver hat. And so forward, in my case, pumps into the ballast tanks, backward pumps out of the ballast tanks. It made the most sense to me. And 255 is the maximum that they can run at through this hat. So we are running them max in for 120,000 milliseconds. Milliseconds, which is equivalent to 2 minutes. And then we stop for a minute and then pump out for 2 minutes and then stop for a minute again. So I just uploaded it. We have it in there. We're going to load in the weights and we're going to run it. Okay, I am reattaching my ballast tanks here. Here. Attach my programming cable. I can reconnect my power cable. I then start a 3-minute timer on my watch. So reset. And in here, I'm gonna reset the Arduino, start the timer. I'm loading 4 of these weight bags. These are adjustable weights from a ankle weight set. So I already have 2 of them loaded into the front. And so those combined with the weight of the battery make up the front of the weight system. So then with everything loaded in, I place in this compression cap. It has this rubber O-ring that gets compressed whenever you tighten this down. And so it sits into there. I then lock it in. I try and get it as tight as possible. That's just, one of the few things that I have within my control, so might as well do it to the best of my ability. Something that I would love to get the opportunity to do is replace every single zip tie on here. They are functional at the moment, but some of them I've taken on and off just through the testing process enough times that they're starting to get loose or not gripping as well as they should. So I'm at a minute 20 left, so let's head over to the tub. All right, so 50 seconds left. I've already got it in the water. So because, as I've mentioned, our ballast tanks are pre-filled with water, it does give them a tendency to either pool at the front or the back of the ballast tank. The central cavity of the robot does seem to be fairly well balanced, and I can tell this because I can pitch it forward and get the ballast tank to shift. And that almost gives me like a little bit of like decision-making control over how the robot sits. For the sake of this experiment, I think it's gonna sit better on the back right there. And so I really think with the 2-minute time period, oh, notification on my watch. All right, there we go. And the timer goes off. So now we have a 2-minute time with the pumps running, and I'm gonna go ahead and pitch it forward for this. And really we're just looking for it to reach a state of neutral buoyancy. And so we can kind of already tell we're right around there, like we're floating really close. It's hard to tell in this configuration how it would behave in a deeper body of water. Would it still float this close to the surface, or because it's interacting with the bottom, is that why it wants to float like this? But it is confidently floating right now. And then at the end of the 2 minutes, I'm gonna manipulate it again, and we'll see if it will sit on the bottom, which should tell us that we're pretty close to either neutral buoyancy or negative buoyancy where it wants to sink. All right, with 10 seconds left, this is about how it seems to be sitting. Once the timer goes off, I'm gonna manipulate it in the water, and we'll see if we're closer to that neutral buoyancy. This is the best way of telling, in my opinion, just simply because because I have such a shallow. Yeah, okay. So it'll sit. I've got another 2 minutes before the pumps start running in the opposite direction, and so I will bring you back then. All right, about 15 seconds left. 10. And I'll let you be with me for the entire time, since we should see a distinct change. It should either rock up or forward with once the buoyancy takes over. So we're not seeing any bubbles out of our pumps, which is a good sign that we're actually pumping water out and not just air, which I have had problems with that previously. I'm gonna check the outputs. Yep, they're pumping out. It's so quiet, especially once it's underwater. I obviously have the weight really close to neutral buoyancy. Like, I am very close. And so I would imagine that with this 2 minutes, I should be hitting either just above buoyant and just below neutrally buoyant, which can, especially in a bathtub of this depth, can be really hard to distinguish the difference from my understanding and my experience so far. 30 seconds left. We'll see if it does anything. It'll for sure pitch up or rock back like I've been showing, just because that's what it will do on its own. But I have had it do it off of the bathtub floor on its own without having to be disturbed. I don't know. It's very light and easy to move in the water, so I'm not concerned about having to overcome either too much weight or too little weight with thrusters. Although I'm sure for retrievability purposes, it would be preferable if it could fully submerge to the surface without having to use the thrusters. I'm just gonna, yeah, it wants to float. It's just, it takes an object in motion will stay in motion. We're having to fight some laws of physics here in order to get it to, and I would bet that right now I would have a much harder time getting it to sit in that stable position. Yep. Yeah, so there it is, back at that stable position. But it takes next to nothing to get it to come all the way to the surface. And right here, it's barely touching the ground. And it'll come up, but yeah. That's what I got.